All right, this is my third trial. Hopefully this works. So this week we're going to focus on solving trig equations using identities. We worked with solving trig equations pretty much all of April, and then all of May so far we focused on using trig identities. So now this last week we're going to mesh those two topics together and see how it goes. So today we're going to focus on just using some of the simpler identities, so Pythagorean, reciprocal, quotient, just to start. So in this first example, we see that we have cosine of x multiplying a cosecant of x equaling a 2 cosine of x. I see that I have cosine of x on both sides, so I am tempted to divide cosine of x on both sides. However, I will not do that because I would then forget about finding some solutions that are based off of cosine. So whenever I see something like that, when I see like terms, but they're on opposite sides of an equation, I'm going to group them on the same side. So I'm going to go ahead and rewrite this equation into cosine of x multiplying cosecant of x minus 2 cosine of x. And I want that to equal 0 then. Because I do this so that way I can factor, and then I can rewrite that as cosine of x times a cosecant of x minus 2, and that should equal 0. Right? Because now that I have a factored term equaling 0, the zero product property that we've been using for a couple years now comes into play. So I'm trying to solve two problems. I'm trying to figure out where cosine of x would equal 0, and when cosecant of x minus cosecant of x minus 2 would equal 0. Right? So that's why I don't divide the cosine, because if I did, then I would have completely forgotten about that possibility right there. Right? So I'm going to go ahead and solve that real quick. I know that cosine of x is equal to 0 when x is equal to pi divided by 2. And because I don't have an interval that I'm trying to find solutions, I need to generalize it. So I'm going to say plus 2n pi, where again, n represents integer values. But pi over 2 is not the only principal angle where cosine of x will equal 0. I also should remember that cosine of x is equal to 0 at 3 pi over 2. Then plus 2n pi. Right? So that's the answer for just this part of the problem. Again, when I solve this, I think about finding principal angles. I know that typically there should be two solutions to a problem. The only exception being whenever cosine of x or sine of x is equal to a positive or a negative 1. Or if the answer is outside the range of a cosine or a sine function. All right. For the cosecant, that means that cosecant of x should equal 2. But that doesn't help me because I don't really know my cosecant that well. I do know my sine, though. So because I know sine is the reciprocal of cosecant, I could rewrite this problem to be sine of x, the reciprocal on the left, should equal the reciprocal on the right. And if I'm talking about where sine of x is going to equal a half, I know my unit circle, so I know that's going to be at pi over 6. Generalize it. And I also know that's going to occur at 5 pi over 6 because sine is positive in the first and second quadrant. And those are the two angles where sine of x would equal a positive 1/2. And again, adding the 2 and pi to generalize my solutions. So when you see something like that, group them, factor, set equal to 0, and solve for x. All right, so if we now take a look at the next one in the middle, this one's a little different but a little similar. So in this problem, I see that I have cosecant squareds, so I'm going to avoid. All right, actually I had to change this problem because if I want to work out the way it does, this is what I need to work with. So in this situation, I have cosecant squared on both sides, so I need to group my cosecants. I can't get it equal to 0 because of that 4, and I'm okay with that. Because here's what's going to happen. When I move that over, I'm going to have a 3 cosecant squared of t is going to equal a 4. Which means that cosecant squared of t should equal 4/3. Which means that sine squared of t should equal 3/4. 3/4. Which means that sine of t should equal the square root of 3/4, which would be the same as square root of 3 divided by 2. All right. But I made a little mistake, and it's the one that everyone is going to make. So don't do this. I just took a square root. When I take a square root, I should have both positive and negative. So it should be plus or minus the square root of 3/4, which means I'm looking for plus or minus the square root of 3 divided by 2. Ha! So I'm looking for wherever sine of t will equal either a positive radical 3 over 2 or a negative radical 3 over 2. And so knowing my unit circle, I know that t should be pi over 3, generalizing it, plus 2n pi. It should be 2 pi over 3 plus 2n pi. It should be 4 pi over 3 plus 2n pi. And it should be 5 pi over 3 plus 2n pi. Always make sure that when you apply a square root, you take into account both the positive and the negative version of that square rooted value. So notice, in this instance, I should have 4 distinct principal angles. All right. So last one. Let's get some room going. If you notice, I've used a lot of my reciprocal identities so far. Now we're going to go ahead and try something different. So in this problem, I have a cosine squared minus a sine squared equals a 3 cosine of x minus 2. Because I have the cosine of x on the right side, it's in my best interest to rewrite everything in terms of cosine, specifically in terms of cosine of x. So I'm going to choose to look at this as cosine squared of x minus 1 minus cosine squared of x. That's my Pythagorean identity. That should equal 3 cosine of x minus 2. So then if I simplify the left side, I would have 2 cosine squared of x minus 1 equals 3 cosine of x minus 2. So then rewriting that, because I have it all in terms of cosine of x, I want them all on the same side. And I'm going to do a little bit of factoring while I'm at it. So cosine squared of x minus a 3 cosine of x plus 1 should equal 0, right? And if you go back to that u substitution stuff we were doing, this is really looking at the problem 2u squared minus 3u plus 1 is equal to 0, which you can then factor into 2u minus 1, u minus 1 equals 0. So then that means 2u minus 1 should equal 0. So u should equal a positive 1/2. Or u minus 1 equals 0, meaning u should equal 1. But again, since we used u to replace the cosine of x's, that means I'm looking for where cosine of x will equal a 1/2, and where cosine of x should equal 1. So using my my knowledge of the unit circle, cosine's equal to a 1/2 at pi over 3. Generalizing it because they didn't give me a specific interval to work with, there's that. The only other principal angle should be 5 pi over 3 because cosine's positive in the fourth quadrant. Generalizing it because I didn't have a specific interval that I'm looking for answers for. So there's that. And if I think about where cosine of x will equal 1, well, at x equals 0 plus 2n pi. However, this one is a special case because there's only one solution and it's 0. So I could just say it's going to be at x equals 2n pi. Again, as long as n represents an integer multiple. So every time that I start at 0 and I complete an entire rotation, cosine will equal 1. And that's how you approach these problems. I know that some of you guys may look at this last one using a double angle identity, but it is in your best interest to make sure that the input to your trig functions are the same, meaning that you don't want to have to work with cosine of 2x minus cosine of x plus 2 is equal to 0, because if these are not the same, then you can't do any factoring. You're going to have to rewrite anyways. So you might as well avoid that step at the get-go. You could do it that way, but it's going to be more work. Thank you for coming to my TED Talk.